students. Now I'm going to explain about crystal field stabilization energy in tetrahedral complexes. As we discussed earlier, the crystal field stabilization energy is the energy required to fill the electrons in lower energy levels. That means T to G set of orbitals in octahedral complexes, E set of orbitals in tetrahedral complexes, right? So now we are going to explain about crystal field splitting energy in tetrahedral complexes. The formula is minus 0.6x plus 0.4y delta T MP. Here we go through the terminology. X is number of electrons in E set of orbitals and Y is number of electrons in T2 set of orbitals. Delta T is crystal field splitting energy in tetrahedral complexes and M is number of electron pairs and P is pairing energy. Let us go for an example. Strong field complex tetracyanonickelate 2, nickel with atomic number 28 and electron configuration is like argon 3d8 4s2, right? So nickel is with +2 oxidation state, that's why we are taking D8 system, and the obtaining electron configuration is E4T2 4, right? So by calculating CFSE, minus 0.6 into electrons in E set, that is 4, 0.4 into electrons in T2 set, delta T plus, and if we see in the configuration, there are 3 electron pairs into pairing energy, right? To calculate CFSC, we will get the value minus 0.8 delta T plus 3 electron pairs into pairing energy. If we see another example, tetrachloroferrate 2 weak field complex. Iron is with a 26 atomic number, having electron configuration argon 3d6 4s2, and when iron is +2 oxidation in the complex, it is having d6 system with E3 T2 3 electron configuration. If we calculate CFSE, minus 0.6 into electrons in E set, that is 3, 0.4 into electrons in T2 set, that is 3, delta T plus 1 electron pair into pairing energy. So by calculate this, we will get minus 0.6 delta T plus 1 pair. If we see the tabular form of CFSE calculations in tetrahedral complexes, here I have mentioned the electronic system. If it is weak field complex, then the configuration, calculated CFSE. If it is strong field complex, the electron configuration and calculated CFS, right? So for D1, for weak field complex, electron configuration is E1T20 and CFSE would be minus 0.6 delta T. Of course, for strong field complex also E1T20, CFSE would be minus 0.6 delta T. For D2, configuration is E2T20, the CFSE is minus 1.2 delta T. For strong field complex also, the electron configuration is E2T20 and the calculated CFSE is minus 1.2 delta T. For D3 configuration, for weak field complex, the electron configuration is E2T21. Calculated CFSE minus 0.8 delta T. For strong field complex, the pairing will take place. Therefore, E3T20 will be the electron configuration and the CFSE is minus 1.8 delta T plus 1 electron pair into pairing energy. For D4 electron system, the electron configuration for the weak field complex is E2T22 and the calculated CFSE is minus 0.4 delta T. For strong field complex, the electron configuration is E4T20. Electron pairing will be takes place in the strong field complexes, and violence of Hund's rule will takes place here, right? And the calculated CFSE is minus 2.4 delta T plus 2 electron pairs into pairing energy. For D5 system, for weak field complex, the electronic configuration is E2T23 and the calculated CFSE is 0. And for strong field complexes, the electronic configuration is E4T21 and the CFSE is minus 2 delta T plus 2P. For D6 electronic system, the electron configuration for weak field complex E3T23 and the calculated CFSE is minus 0.6 delta T plus 1 pair. For strong field complex E4T22 and the calculated CFSE is minus 1.6 delta T plus 2 pairs. And for D7 system, the electron configuration for weak field complex is E4T23 and the CFSE is minus 1.2 delta T plus 2P. And the electronic configuration for strong field complex is E4T23 and the calculated CFSE is minus 1.2 delta T plus 2 pairs. For D8 system, the electronic configuration for weak field complex is E4T24 and the calculated CFSE is minus 0.8 delta T plus 3 electron pairs into pairing energy. And for strong field complexes, electron configuration is E4T24 and the calculated CFSE is minus 0.8 delta T plus 3 electron pairs into pairing energy. For D9 system, E4T25 will be the electron configuration minus 0.4 delta T plus 4 electron pairs into pairing energy. And for strong field complexes, electron configuration would be E4T25 and the calculated CFSE value is minus 0.4 delta T plus 4 pairs. D10 system, the electron configuration for weak field complexes is E4T26 and the calculated CFSE is 5 electron pairs into pairing energy. For strong field complex also, E4T26 will be the electron configuration and the calculated CFSE is 5p. If we see the CFSE values for weak field complexes up to D1 to D5, D1, D2, D3 and D4, D6, D7, D8, D10. So D1 and D6 varies with minus 0.6 delta T plus only one pair will add into D6 system. And D2, D7 also having the same CFSE with difference of number of electron pairs. D3, D8 also having same CFSE value with the difference of number of electron pairs. D4, D9 also having same CFSE values with the difference of number of electron pairs. Right? For weak field complexities. And one more observation is from D6 configuration, D6 to D10, for weak field complex and strong field complexes, we are having same CFSE values for both weak field complexes and strong field complexes in tetrahedral complexes. The people who are preparing for the competitive examinations, these observations you should notice for your benefit of time.